Okay.
Ah, there we go.
Woohoo! Charles Doran. Woohoo! That was our introduction.
Okay. Well, thank you very much. It's a pleasure to give the very last lecture of this special HMS semester. I'm going to adhere, if anything, more strongly to the words of encouragement from the organizers to keep things very low-tech and accessible today. Also, there's going to be a little bit of need to do that because Alan Thompson gave a talk on some of what I'm going to be talking about in the mirror symmetry seminar just a few weeks ago. So I don't want to repeat too much of what he said, although there will be some repetition inevitably. Okay, so the title today is different. It's Calabi-Yau fibrations, construction and classification. Now last time, we studied the interplay between the geometry and moduli of Calabi-Yau manifolds and periods and Picard-Fuchs equations. Okay. So today, we want to take a slightly different approach, making use of what we did last time, and we want to look at what I would call the internal structure for both Picard-Fuchs differential equations and Calabi-Yau manifolds. Okay. And this is going to give us a means of construction and classification. I'll say from the inside out. Okay. So let me start with a basic result about Calabi-Yau manifolds that is surprisingly overlooked in the literature. I mean, it's a very, very basic result. It's one I first stumbled on when I was a grad student, just playing around with adjunction. And it's kind of obvious to the experts, but it's really quite important. So this basic result is about the hereditary nature of Calabi-Yau fibrations. Okay? And the basic principle is very simple. So proposition, if S contained in W is a smooth Calabi-Yau d-1 fold hypersurface in a d-dimensional Calabi-Yau manifold W, then the linear system S is base point free and hence there exists a map pi W to P1 with S as a fiber. Okay, so what does that mean? That means if you have a Calabi-Yau submanifold in Codimension 1, you actually have a fibration. Okay? So this is, this is a really, really kind of important result. It's saying that if you nest your Calabi-Yau manifolds, for example, like these Matryoshka dolls, the Russian dolls, okay, then what you actually get is an iterated Calabi-Yau fibration. So just having a flag of Calabi-Yaus is enough to give you this iterated fibration structure. Okay, so proof. So by adjunction, OS of S is the relative normal bundle, which is the canonical bundle, which is OS. Okay, let's let iota S embedding into W be the inclusion. Then we have a short exact sequence of sheaves. 0, OW, call this map S, OW of capital S, pull back OS, 0, with little s a section of OWS, whose vanishing locus is S. Okay. So the short exact sequence gives rise to a long exact sequence in cohomology. 0 goes to H0 W OW, goes to H0 W OW of S, goes to H0 W iota upper star OS, goes to 0. And the vanishing of H1 WOW follows from the Calabi-Yau property of W. Okay? So from this, we see that the restriction of a generic section of OW of S to S is a non-zero section of iota upper star OS, which is non-vanishing. Okay, so thus, linear system of S is base point free and determines a map W to P1 since H0 OW of S is equal to 2 by the exact sequence. Okay, so really easy, really basic result, but writ large, what it's telling you is that when a Calabi-Yau manifold contains a Calabi-Yau submanifold, you can expect to see a fibration. Now, of course, I cheat a little bit. This is Codimension 1, right? Calabi-Yau in Codimension 1, you get a fibration to P1. But what often happens is that these you get a chain, a nesting, a flag of Calabi-Yau submanifolds, and that's where you see your fibration structures. Okay, now the way I stated it, and I guess technically the way I proved it, I don't quite allow for the extreme case where W is dimension 1 and S is possibly disconnected. In particular, it could be 2 points, as we saw last time, or a double point, right? So let's just check to see that this philosophy coming from this theorem, this proposition still applies. So first of all, just note the phenomenon is more general, e.g. applies to certain singular S, W, dot. Okay, but now let's do an example, and the example is, which, as I said, is not strictly speaking an application of the proof of the proposition, the example of D equal 1. Okay, so we have an elliptic curve with either 2 distinct marked points or 1 double point. Okay, so what on earth must this analogous proposition be telling us? Well, it's telling us that somehow you have an elliptic curve, you specify 2 points on that elliptic curve, or a single double point on the elliptic curve, and you get for free a presentation of the elliptic curve as a double cover of CP1 branched over 4 points. okay, where the double point would be one of the the fibers over those 4 points, and the 2 marked points would be a quote-unquote smooth fiber, okay? So why should this be true? Well, it's got to be true for really dead easy reasons, and it's such a fundamental observation. It's got to be true for reasons that go all the way back to the origin of an elliptic curve. So let's take this double point case, because that's the one people are more familiar with in this setting, and let's go back to Weierstrass. Okay, the Weierstrass model for elliptic curves. Now, remember, Weierstrass gave that beautiful equation, y squared equals 4x cubed minus g2x minus g3. But there were really good reasons for the normalization he picked. And the really good reasons had to do with the fact that x was the Weierstrass pay function and y was its derivative. Okay? So, in any case, the really good reasons have to do with the uniformization of an elliptic curve E by the Weierstrass pay z tau function. Okay, so think back to your graduate coursework in elliptic function theory. In my case, that would be Noam Elke's course, 213. Okay, and how was the Weierstrass pay function introduced? Well, it was introduced as a doubly periodic function on the complex plane, subject to certain rules. And the rule was the existence of a pole of order 2 at one point in a fundamental domain with trivial residue. Okay? That is exactly the condition we're talking about here. And once you have it, you have the Weierstrass pay function everywhere, including its tau dependence. In other words, your family's determined. Okay? So your fibration is determined, your fibration, your map from your elliptic curve double cover to CP1 is determined, and in fact it's determined complete with its tau dependence. Okay, so that's that case. What about the 2 marked points? So that's this one. Okay, what about the 2 marked points case? Well, the 2 marked points case is even older. So it's Jacobi's model for elliptic curves. Okay, and the function involved here is uniformization of E by what's called the sinus amplitudinous, sin amp. Okay, so sin amp is the inverse to the multivalued morphism that goes t goes to the integral 0 to t dx over the square root of 1 minus x squared, 1 minus k or kappa squared x squared. Okay, it's the inverse to that. And again, it defines E 2 to 1 over P1 branched this time over plus or minus 1 over k with moduli. Okay? So it's kind of an afterthought of the uniformization, but it's important. Okay? So you think of uniformization only going from the complex plane down to the 2 torus, complex plane down to the elliptic curve. But in fact, that's not right, because the functions we're defining, like the sinus amplitudinous, start with a variable moving on P1. Okay? And when you fully invert, you actually recover not just the map down to the elliptic curve, but the map also all the way down to that P1, and that's the 2 to 1 cover. Okay? So this classical fact, it doesn't get any more classical than that when it comes to Calabi-Yaus. This classical fact is the same fact, that Calabi-Yau, Codimension 1 Calabi-Yaus induce Calabi-Yau fibrations. Okay. So what this suggests is that we think in terms of construction and maybe classification of Calabi-Yaus in terms of iterative construction of Calabi-Yau manifolds, starting with the simplest case. Now, is the simplest case elliptic curves? No. I just said the simplest case is not. The simplest case is a family of pairs of points. So starting with a family of pairs of points. All right. So we're going to do this, and we're going to do this both on the level of periods and Picard-Fuchs differential equations, but also on the level of geometry. And by doing it together, hand in hand, you're going to maintain that tight relationship between the sort of control of the periods and control of the geometric object that gives rise to them. All right. White chalk. Can I get more white chalk, maybe? Oh, I see, it's right over there. Must be there.
Do you need
I can use some, yeah. It's easier to erase. Okay, thanks. All right, so what next? Yes, so let's start. So start. Okay. So I'm going to write down a ramified family of pairs of points, okay? So I'm looking at y naught squared equals 1 minus t, where t is in C. Okay? Doesn't get simpler than that. What is our notion of period here? Well, I claim it's a function with branch cut, reciprocal of y naught. That's the period, okay? Now, if I adjust this branch cut to coincide with the t from 1 to infinity, okay, then this function is holomorphic in a punctured disk about t equals 0. Okay? And then I can rewrite this function, 1 over y naught, as a hypergeometric function, 1f0 type, which is allowed in the n plus 1 fn formalism for hypergeometric functions. 1/2 semicolon empty set t, okay? This is terrible notation, but it's consistent. That's a semicolon, and that's nothing. Okay. Well, because it's an f0, 1f0, okay? All right, and what is that? That's just 1 over the square root of 1 minus t. So it doesn't get any easier than this, okay? Now, the game in terms of the relationship between periods and Picard-Fuchs operators is that the Picard-Fuchs operator has to annihilate the periods. So the period is annihilated by, well, it's a first order degree 1 Picard-Fuchs operator. I'll call it L sub 1. It's theta minus t times theta plus 1/2. Okay? And here, theta is as before t dgt. In fact, I might have called that script delta yesterday. And then if you want to be really pedantic here, you could say, well, wait a minute, this is giving us a rank 1 local system, so what are the monodromies about the regular singular points for this rank 1 local system? And the regular singularities, well, it's of hypergeometric type, are 0, 1, and infinity, and the corresponding monodromies are 1, so the identity, -1 and -1. That's it. Okay? Now, what we want to do is to pass from this example to a family of elliptic curves. In other words, we want to bootstrap from the lower dimensional Calabi-Yau families to higher dimensional Calabi-Yau families. Okay? And the first step to doing that is to promote the deformation variable. So promote the family base parameter to an additional complex sort of spatial variable, fiber variable, x. In other words, so i.e., I want t to become x, okay, in the original family, okay? And I also want to do what is called a quadratic twist. Okay, and the quadratic twist has this marvelous property of preventing the regular singular points from proliferating. It's going to keep you all concentrated on 0, 1, and infinity, which is not necessarily always a goal, but it's a goal for simplicity if you're trying to construct higher rank, say, hypergeometric variations. And the quadratic twist here is, say, replace y0 squared with minus y1 squared over x times x minus t. Okay, quadratic because, well, it's degree 2. Okay, so if I actually do this, starting from our initial equation for the family of pairs of points, let's see what happens.
Where does this quadratic twist come from?
I'm sorry?
Where does this quadratic twist come from?
So the way you should think of the quadratic twist is, well, there's different ways of thinking about it. But the way I would encourage you to think about it is that the quadratic twist is permitting you to increase the complexity of the family, algebraically, without increasing the size of the base locus, the branch locus, or the unbranched locus, the locus of singular fibers. Okay, this is intuitively what it's doing. In practice, quadratic twists are sort of well understood in the context of elliptic surface families, or elliptic surfaces. What a quadratic twist does is it takes you from one elliptic surface to another elliptic surface, where two of the fibers in the original elliptic surface now have starred monodromy. Okay, so what it's doing is it's in Kodaira's sense. So what it's doing is it's taking the local monodromy and multiplying it through by the minus identity matrix. So IN goes to IN star, type 4 goes to type 2 star, type 3 goes to type 3 star, etc. And you're doing that at 2 points. So you think of this as analogous to a base change, but not really. It's the same base. And it's, pardon?
So you should think of it as some kind of an operation on the monodromy representation of like a...
Yeah, you can think of it as an operational monodromy representation, except of course that it has an implication for the geometry of the pencil. Right. So, but it definitely has the property that its behavior on the monodromy representation is concentrated at 2 fibers. So if one of the fibers that you're applying it to is an I0, a smooth fiber, then suddenly it becomes an I0 star, which is a D4 fiber. Okay, so it's a rather serious change. You go from being smooth to being, D4 type. Nevertheless, from the standpoint of the monodromy representation, it's very modest. And what it's actually doing is it's playing off the PSL2Z versus SL2Z properties for the monodromy representation. So, yeah, so from the standpoint of the functional invariant, the J function, as we were talking about last time, you'd see no change. It's only detected by the homological invariant.
This is an operation you can do. I mean, is this generalized? You can elliptic. So this generalized to any.
This generalizes to any. Yeah. So what I'm encouraging, the reason why I didn't introduce it that way is I'm encouraging you to think of it as merely a variable substitution. Okay? Because this is going to percolate through at every step. Okay. And more generally, there's going to be a mixture of this kind of quadratic transformation with various well-chosen base changes that are going to allow us to see a great variety of complexity emerge from one very simple example, which is this family of pairs of points.
So just let me, you're saying that you're going to control your periods, right, and stuff like that inductively. Mm-hmm. And you're saying that this actually comes somehow from the fact that the description you gave before about like a Calabi-Yau flag, right?
Yeah.
you're saying that you can construct, so each one of these Calabi-Yau flags is some kind of a monodromy representation on the lower dimension Calabi-Yau, even geometric, and you were saying that you can actually construct these
I'm saying you can
construct.
construct, you can construct the higher dimensional manifolds with the flag from the lower dimensional with their flags. And you control the monodromy each way.
All the way.
All the way up. All the way up. Yeah. Okay, so I'm doing the absolute, I would say, dead simplest example right now. Okay, just so you see how it works in the simple case. Then we'll do some more complicated examples. Okay. So, okay, I was erasing. Yeah, and of course, a reference for what I'm talking about right now is my paper with Malmendier, which has a title, something about symplectically rigid Calabi-Yaus, but the title is misleading, perhaps. I mean, it's really about this kind of iterative construction procedure. Okay, so let's just do it by hand. We'll see what happens. So we have y naught squared equals 1 minus t. This is what we're starting with, okay? And then we're going to do this substitution that we're talking about here. The t goes to x in the quadratic twist. So this becomes what? Minus y1 squared over x minus t equals 1 minus x, because t was related to x. All right, so I multiply through and switch the minus sign on the other side, and I get y1 squared is equal to x times x minus 1 times x minus t. And this has a name. This is the Legendre family. Or Legendre pencil of elliptic curves. Okay? So what's happening Hodge theoretically okay, in that sort of hierarchy we were talking about geometry, Hodge theory, differential equations. So Hodge theoretically, I got to give this a name. I'll call these x sub t, or t in p1 minus 3 points. p1 minus 0, 1, infinity. Okay? So Hodge theoretically, h1 xtc gives rise to a flat vector bundle, which is nothing more than R1 pi lower star C. Okay. There's a polarization on the Hodge filtration on Hz, which is H1 XTZ, with two steps. So we have Hz, we have Q, and we have F1 contained in F0, which is Hz tensor C. Okay, so what is everything here? Well, Hz I defined. Q comes from the cut product. Okay, F1 is really just H10 of xt, and it's spanned by dx over y1. Okay? Or if this were not going to be an iterative procedure, I would have called it just y, and it would be your standard dx over y. Okay? So now, what are the periods? The periods of this dx over y1, well, I mean, this is a familiar story. It's the story from the Legendre elliptic curve. But let me just repeat it. So periods of dx over y1 over a basis of 1 cycles, you know, like an A cycle and a B cycle, satisfy hypergeometric 2f1 1 half semicolon 1 t. Okay. And the holomorphic solution near t equals 0 is the period integral over, I don't know, a cycle, which I'm going to call sigma 1. I'll define in a second. So it's the integral over sigma 1 dx over y1, integral from 0 to t dx over root x times x minus 1 times x minus t, which is pi I times 2f1, 1 half, 1 half, 1 t. Okay? Now, what's sigma 1? Okay, well, this is where you have to be a little careful, even in this dimension. So it's a closed cycle about the branch points at x equals 0 and t. And even in this dimension, you have to play a little bit, right? Because you want to deform that into a branch cut. So you deform into a branch cut from x equals 0 to x equal t on one of the y sheets and returning on the second. Okay, so nothing you haven't seen before, but I'm explaining it in detail because this step generalizes in the next dimension. Okay, now, just as before, the period is annihilated by this second order degree 1 Picard-Fuchs equation, so by Pf dE. I'll call it L sub 2, which is theta squared minus t theta plus 1/2 squared. All right, so far so good. So geometrically, we built an elliptic curve from a family of pairs of points, okay? Now, there ought to be a relationship, perhaps not as obvious, between the periods for the family of elliptic curves and the periods for the family of pairs of points. Okay, so how to relate periods? We need a relationship between 2f1 and the 1f0. Okay, so the answer, there's lots of answers, but here's an answer. Answer is what's known as the Hadamard product. Hadamard product. Okay, so the Hadamard product takes as its starting point a pair of power series. F of t equals sum n greater than or equals 0, fn t to the n. G of t equals sum n greater than or equals 0, gn t to the n. Okay? And it's a way of combining them. Now, it is not the intelligent way that we teach our students in complex analysis class. Okay? It is quite opposite. It is exactly the way that students make mistakes in multiplying power series. So f star g of t is the sum n greater than or equals 0, fn times gn t to the n. Okay, that's Hadamard was a brilliant man and came up with this. No, there's a method to this madness. And so, what does this buy us? Well, it buys us the following formula: 1f0, 1/2 t star 1f0, 1/2 t is equal to 2f1, 1/2, 1/2, 1 t. Now, this notion of Hadamard product also applies to hypergeometric series, and so the Hadamard product then with index 1/2 applied to L1 produces L2. Okay. All right, so that's probably all I want to say. I'm passing from the pairs of points to elliptic curves. Now let's go from elliptic curves to K3 surfaces. So I want to do something completely analogous, okay? I'm going to promote my variable t to u now, and I'm going to do this kind of quadratic twist, y1 squared as before, now y2 squared over u times u minus t. Okay? And what I get from this, starting from the Legendre family, is y2 squared equals x times x minus 1 times x minus u times u times u minus t, okay, known as the twisted Legendre pencil. Okay? And this was reasonably well studied in I don't know, maybe the late 60s, early 70s. But in any case, it's a Néron model for a family of elliptically fibered K3 surfaces xt. I'm going to keep the same name, x sub t. I'm not going to keep replacing my family name each time I go up a dimension. Xt of Picard rank 19, generically. And that's elliptically fibered with section. In case you're wondering. Over P1. Okay, so pi from x to P1. And Hoyt and Endo, following work of Shimura and Eichler, showed that the rank 3 parabolic cohomology, as we defined it last time, has a natural polarized Hodge filtration. Okay. So let's describe that. HZ, Q, F2 contained in F1, contained in F0, which is HZ tensor C. Okay, so let's see what everything here is. So this one, F0, is spanned by suitable meromorphic differentials of the second kind. Okay. This Q polarization is a non-degenerate, rational valued bilinear form determined by the period relations for our 2-0 form, which in this case is du wedge dx over y2. F2 then is the cone q equals 0. F1 is the tangent plane to the cone along F2. Okay, so this is the story there. In practical terms, you write it out and you get that q is equal to, well, there's an evenness thing, so 2 z1 squared plus 2 z2 squared minus 2 z3 squared. And you see the signature, the mixed signature, 1 comma 2 or 2 comma 1. Okay, then you write it. And the local system, V, which now is R2 pi lower star C, is irreducible. And HZ comes with a pure Hodge structure of weight 2 and type 1, 1, 1 with HD tensor C being just H20 plus H11 plus H02. All right. And as before, where we had to mark that A cycle, I labeled sigma 1, and we had to actually worry about deforming it into the branch cut. Okay? As before, that's what I mean by as before, we can construct a basis of transcendental cycles from, well, cycles in the fiber and well-chosen paths in the base. So from cycles in the elliptic curve fiber plus well-chosen paths in the base connecting 0, 1, t, and infinity. Okay. So once you have your basis of transcendental cycles, you now can construct these period integrals. So you do periods of the holomorphic 2 form du wedge dx over y2 over these transcendental cycles satisfy a third order Picard-Fuchs differential equation. And it's nothing but 3f2, 1 half, 1 half, 1 half, 1, 1, t. Now, this particular fact, maybe I'll leave that one up, follows from a classical formula called the Euler integral transform formula. So this follows from Euler integral transform formula. And it expresses the integral here. Integral 0 to t du over the square root u minus t 2f1 1 half 1 half 1 bar u is pi I times 3f2 1 half 1 half 1 half 1 1 t. Okay, so this is sort of a literal bootstrap from one to the next. Right, and so this period is annihilated by this same equation, okay? So annihilated by L3, theta cubed minus t, theta plus 1 half cubed, with Hadamard product representation. Okay, so this is kind of fun. So there's the Hadamard product for the 2f1, and now I go 1f0, 1 half bar t, star, 2f1, 1 half 1 half 1 t is equal to 3f2, 1 half 1 half 1 half 1 1 t, which at this point should not be a surprise. Okay. So we get a pencil of elliptically and Picard rank 19 K3 surface fibered Calabi-Yau threefolds. Okay. All right. So said Calabi-Yau threefolds, I don't mean that yet. We're only up to Picard-Break 19 K3 surface fibers. Okay. Next step is going to be threefolds. Okay, but now, so now we want to go up to threefolds. So that'll be our next step. And again, for this particular family, this is not all that difficult. Okay, so we have our family of K3s. Okay, and each x sub t is okay. So what do we want to do? Okay, that's what I want to do. So next step, yeah. Okay, so the next step pass to Calabi-Yau threefolds. Okay. So t is going to go to s, and y2 squared is going to go to y3 squared over s times s minus t. Okay, and this is going to give us a family xt given by y3 squared equals x times x minus 1 times x minus u times u times u minus s times s minus t. Okay. So now it is actually, so we get a pencil of Calabi-Yau threefolds that are simultaneously containing over u and so y. Okay, so fibered by elliptic curves over a two-dimensional base, actually CP2, and affine coordinate u and s, okay, and fibered by Picard rank 19 K3 surfaces over P1 with affine coordinates, coordinate u. Okay, and then we have the same kind of story, right? We're going to have we have R3 pi lower star c, giving us a pure Hodge structure of weight 3 and type 1, 1, 1, 1. Okay, now we're going to have the splitting HZ tensor C as H30 plus H21 plus H12 plus H03. Okay, this is the Hodge structure on the parabolic cohomologic group of XT given in terms of the periods and period relations for the three form. Now the holomorphic three form is ds wedge du wedge dx over y3. Okay, and the periods satisfy for F3, 1/2, 1/2, 1/2, 1/2, 1, 1, 1, t. Okay? And again, we apply the Euler integral transform argument, and again we find that there's an expression for this in terms of a Hadamard product with 1F0, 1/2 t, that relates it back to the 3F2. Okay. So this whole procedure is what Andreas and I call pure twist. Okay. Because in effect, we're doing this quadratic twist operation, the promotion of variable, of course, but the quadratic twist operation, but we're not doing any additional base change. And that is precisely why the Hadamard products are behaving in such a silly fashion, right? That the holomorphic period is nothing but the Hadamard product of 1F0 with what came before, okay, from the fibers. More generally, we have to work with something that we call mixed twist. meaning we like quadratic twists, but, and what they do for us in terms of maintaining the hypergeometric character of these variations, but we need to allow ourselves a more complicated base change to be composed with it, okay? So this is just compose with suitably chosen base change. Okay. Now I should also say, for a large class of extremely important examples, you can do this without the twist and just do a base change. Okay, and much of what we're talking about will still go through, but it's at an expense, and the expense is that you're going to have a proliferation of regular singularities. So the advantage of the quadratic twist is that it keeps you to have a few of them. Okay, so how does this mixed twist work? Well, so we start, let's go back to the beginning and start with pairs of points. Okay? And starting from my pairs of points, I want to specify a triple of integers, I, j, and alpha, okay, where I is either 1 or 2, alpha is either 1/2 or 1, and j is between 1 and 2 alpha. Okay? And this, which will determine what we called before, and what we'll talk about soon in generality, are generalized functional invariant. Okay. So in concrete terms, I can build a 2f1 mu 1 minus mu semicolon 1 rt, okay? Which is, of course, a little bit more complicated than the 1/2 that we did before, okay? As an integral, so they have x equal epsilon, dx over x times x plus 1 to the alpha, 1f0, 1/2, nothing, bar. Okay, now this is where the base change comes in, okay? So I'm replacing t now with Cij times t over x to the I, x plus 1 to the j. All right. So if I do this, oh, and I have to say what Cij is. Let's see, did I write that down? I mean, it's just a constant. I'm not sure I wrote it down, but in any case, it's easy to deduce from what I'm writing. It involves I to the j, I to the I, j to the j, I plus j to the I plus j. It's a constant. And some power of -1. Probably, I'm going to guess, it's like -1 to the I plus j times I to the I times j to the j over I plus j to the I plus j. There you go. That's what it is. All right. So, and if I start with my family of points, okay, so point, so t, y squared equals 1 minus t, and I apply this with I, j, alpha, I get elliptic curves of t, y squared equals 1 minus Cij t over x to the I, x plus 1 to the j, times x squared times x minus 1 to the 2 alpha, okay? And I have a little table here, and well, the options, so the options for I, j, alpha, let's put it that way, are 1, 1, 1, 1, 2, 1. I'll do them this way. So the ij alpha are 1, 1, 1, 1, 2, 1, 1, 1, 1/2, and 2, 1, 1/2. Okay, those are the possibilities. And the mu values that correspond to them, I'll put here in the middle, are 1/2, 1/3, 1/4, and 1/6. Okay? And what you get from these are 4 elliptic modular surfaces. And they're the elliptic modular surfaces for the groups G, which is gamma naught of 4, gamma naught of 3, gamma naught of 2, and, basically, I'm going to say gamma naught of 1, but, that's a slight cheat. Anyway. Okay, and in terms of fiber types, the bad fibers, this is I4, I1, I1 star, I3, I1, type 4 star, I2, I1, type 3 star, and I1, I1, type 2 star. So these are precisely, so we get all extremal rational surfaces, elliptic surfaces, with 3 singular fibers. Okay, go back to the list of Person and Pinkham and those guys. And each is a modular surface. So this came from nothing but family of pairs of points and this little bit of data. Okay? So now, with this in mind, you can do the same game, but also with this generalized functional invariant triple dictating properties of the base change. And now you can go from, oops, not good. Now you can go from these families of elliptic curves that are these elliptic modular surfaces to families of K3s. So now,
So when did it do by extreme?
in terms of the Mordell-Weil rank. So this is a classical elliptic surface class of elliptic surfaces, the so-called extremal elliptic surfaces. But in the case of exactly 3 singular fibers, it's a very short list. There's only 4 of them, up to what's called transfer of star. So a transfer of star is a quadratic twist on 2 of the fibers. And of course, if you're already starred, you become unstarred. And if you're unstarred, you become starred. So up to the permutations associated with quadratic twists on those 3 fibers, this is everything. Okay? So now we're going to twist ECT, again with this IJ alpha. And now ECT, which is y squared, I'll put it in Weierstrass form, 4x cubed minus g2 of t x minus g3 of t. Okay, this now becomes this ij alpha k3 sub t. Y squared equals 4x cubed. Now let's see what happens. So we're going from an elliptic surface over CP1, t parameter, to now something which is necessarily going to be K3 fibered by its construction. It's a family of K3s. But each K3 is fibered over the P1. So notationally, we'll write it this way. It's 4x cubed minus g2 of big T, h of u squared x, minus g3 of big T, h of u cubed. Okay? Where the base change is, okay, we have a double cover. Big T equals the Cij little t over u to the I, u plus 1 to j. And then we have the twist. So that's h of u is u squared, u plus 1 to 2 alpha. Okay? So we have both our t dependence and our u dependence.
So when will the Cij?
The Cij is a constant. I believe it is equal to, I have to look it up, but I believe it's equal
to.
Yeah, but it's important. It's a constant dependent entirely on the I and j. So it's literally, I believe, I to the I times j to the j over I plus j to the I plus j. Okay, so it's exactly that constant that determines the funny position of your third regular singular point for hypergeometric ODEs. Right? You know, 0 and infinity, those are okay, fine. You can normalize it to 1, but it's not natural. Hypergeometric ODEs want to have that third point to not be at 1. They want it to be at some special value, and this is basically picking out that special value. Okay, so what we get from this is we get K3s with, well, and now drum roll, Mn equal H plus E8 plus E8, negative definite E8s, plus minus 2n lattice polarizations, where n equal 1, 2, 3, 4, mu equal 1/6, 1/4, 1/3, 1/2. Okay. So we just got 4 of the possible lattice polarizations of Mn type that we were talking about before, which give rise to genus 0 moduli spaces of lattice polarized K3s. Now, you might say, wait a minute, Chuck, there were like 10 of them or something. Okay, yeah. But these are exactly the 4 that have 3 special points. Okay, these are the 4 that are the closest related to the J-line. The J-line is 0, 1, and infinity, or 0, 17, 28, infinity, in any case. And it has orbifold orders 2, 3, and infinity, right? Okay, so these are the analogs of those. All right, so it suffices to just point out at this point, now that we've actually recovered the K3s that we were playing with on Tuesday from this construction, that we can just twist again. Twist again, okay, and use this sort of non-trivial generalized functional invariant, and then we get Calabi-Yau threefolds. So just so you know that this does lead to quote-unquote interesting examples, let me give the example of another astonishingly overlooked in the literature tower of Calabi-Yau fibrations. We did one or so example of this on Tuesday, but let's do the whole tower. So example, the mirror family of degree n plus 1 Calabi-Yau n minus 1 folds. Okay, so let's just check. That works? Yes, this is a degree n plus 1 Calabi-Yau n minus 1 folds in CPN. Okay, so let's give them a name. I'm going to write them in this affine form for the mirror, just as I did before. x1 times times xn times x1 plus plus xn plus 1 plus minus 1 to the n plus 1 t over n plus 1 to the n plus 1 equals 0. Okay? And for n greater than or equal to 2, yt to the n minus 1, so ytn minus 1, is fibered over P1 by hypersurfaces y t tilde n minus 2, with xn as the affine base coordinate. Okay. And just to make it extremely concrete, so special case, we'll do the mirror quintic. Okay, and for the mirror quintic, so we have an M2 polarized K3 fibration, because as we saw, the mirror quartic was M2 polarized, okay? Let's see. All right, okay. And so we have a morphism from P1, I'll call it, okay, I don't want to use my index notation there, so I'll call it P1T, which is the base of the M2 polarized fibration on the Calabi-Yau threefold. 5 to 1 to P1 lambda, which I'm identifying with the moduli space of M2 polarized K3s. Okay? And the formula here is that lambda is some constant, I'm calling it A this time, but in any case, there it is, over T times 1 minus T to the fourth, okay? And its ramification profile, it's ramified to orders, okay, well, ramified, okay, so orders 1 and 4 over the order 4 elliptic point, lambda equals infinity, okay. Order 5 over the cusp, lambda equals 0. Order 2 over the moving point, lambda equals 5 to the 5th times A over, now I'm tempted to write 2 to the 8th, but as I said before, I plus j to the I plus j, I really should write 4 to the 4th. 4 to the 4th, okay? That's the j to the j. And here, ij is equal to 1, 4. Okay. So the modulus is naturally this A value here. Oh, I'm sorry, I didn't write one thing. When I said the general story, I didn't tell you what T tilde was. So let me just put it here. T tilde is equal to minus n to the n t over n plus 1 to the n plus 1 xn plus 1 to the n. Okay? And this is the 1n in terms of the triple ij alpha. Okay? All right. All right, now lest you think that everything is as easy as those Hadamard product computations we showed you earlier, let me just point out that there is a Hadamard product decomposition for periods that comes from the internal fibration structure for this tower, but it is not as dead easy obvious as what you were used to seeing from that pure twist case. So note, okay, the Hadamard product decomposition does follow from the fibration structure, but it is more complicated in mixed twist cases. Okay, so e.g., and now I'm going to do the quintic mirror again. So this is 4f3, and I'll write it on top. 1/5, 2/5, 3/5, 4/5, 1, 1, 1, bar t. Okay, so that we all acknowledge is the holomorphic period for about maximum unipotent monodromy for the mirror quintic. Okay, great. So I should be able to write some kind of decomposition that takes into account the iterative structure that we've been talking about as a Hadamard product. And if everything were naively working the way it did in the pure twist case, you would expect it to be relating a 1f0 and a 3f2, right? Hadamard products, and you'd be done. Okay, no, that's not how it works. What it actually, this is what corresponds to the fibration. You track it through. 4f3, 1/5, 2/5, 3/5, 4/5, 1/3, 2/3, 1/2 T atom product 1F0, 1/2 T atom product 2F1, 1/3, 2/3, 1 T. Okay. In fact, you have to deal with a 4F3 on the right-hand side. Okay. So it's rather sophisticated what's going on, and if you get into the guts of this, you can understand how these non-trivial B values, you have the A's and the B's when you have hypergeometric series, how the non-trivial B values are playing off the non-trivial A values here to make everything work. But again, such a decomposition, there's no reason for it to exist, in my mind, other than the geometric fibration. Okay? A priori, you'd have no reason to expect something like this to exist. There are, in the hypergeometric world, in the linearly rigid world, even in the symplectically rigid world, general arguments you can give based on Tanakian category formalism that suggests that certain decompositions will happen. But there's no geometric content to that, okay? And they're also non-predictive. This, on the other hand, you trace through the geometry and you can derive these formulas, okay? So I'm going to take a 5-minute break, and then we'll spend the last 35 minutes with concluding remarks on classifying fibrations. Okay, so I think it's starting up again. Yes, it's status recording. All right, so let's recap where we are. So I hope I've convinced you that there is a mechanism to simultaneously iteratively construct Calabi-Yau fibrations and their periods. Okay. Now, this does not guarantee that you're going to get all possible Calabi-Yaus by this kind of construction. In fact, it's known that there are Calabi-Yau manifolds that do not possess at least a commutative fibration. Okay. If we move to sort of the non-commutative world, then there's other things we can say. But in any case, the main message here is that for a large class of Calabi-Yaus, this kind of iterative construction works, and that it works in tandem, both geometrically and in terms of periods. So let me state a theorem, which is sort of an experiential theorem, an observation ex post facto. So recall, and I'm not going to repeat this for the umpteenth time, but I'll say recall, and you guys will nod your head saying you remember this. So recall the Doran-Morgan classification of integral VHS of weight 3 Hodge type 1111 Hodge structures, VHS already said, over P1 minus 3 points. Okay? Now, this is a loaded question. You have to know something about it. But in fact, this recovers on the level of RVHS, so on the level of sort of the underlying Picard-Fuchs differential equation, not the integral structures. It recovers the sort of fairly classic list of 14 hypergeometric ODEs of 4F3 type that show up in the literature, in the physics literature, and it's fairly well known. The most famous of these is the 4F3, 1/5, 2/5, 3/5, 4/5, 111 that we were talking about earlier, corresponding to the mirror quintic. So what I'm going to say here is that all 14 of the families of Calabi-Yau threefolds admitting 4F3 hypergeometric Picard-Fuchs equations are in fact fibered by K3 surfaces, each of them is fibered by K3 surfaces, of high Picard rank. Specifically, the lattices, okay, here we go, M1, M2, M3, and M4. Okay, and I left some space because there's 7 cases that are M1 fibered, there's 12 cases that are M2 fibered, there's 9 cases that are M3 fibered, and there's 5 cases that are M4 fibered. And you note that 7 plus 12 plus 9 plus 5 is greater than 14. So obviously there are multiple fibrations of different types on some examples. The quintic mirror, for example, has both M2 and M3. Okay. All right. So in all cases, the moduli space of Mn is identified with P1 minus 3 points. Okay, cusps and elliptic points. And specifically looks like, in this case, P1 with 2, 3, and infinity. Here this is P1 with 2, 4, and infinity. This is P1 with 2, 6, and infinity. And this one is P1 with orbifold points 2, infinite order, and infinite order. Okay, so there's actually 2 cusps there. Okay. And the generalized functional invariant takes the form. Okay, so you go from P1 with coordinates u and t to P1 lambda, which is equal to our moduli space of M and polarized K3s, and it's given by lambda equals a times u to the I plus j over t to the I u minus t to the j. So in other words, all 14 of the examples in that list with Morgan have a uniform construction, iteratively, from exactly the list of Mn-type K3s we constructed from pairs of points with this mixed twist construction. Okay? All 14. Now, let me just emphasize how crazy this is, because the original reason that that list was cooked up was because we were not looking for necessarily regularities among H21 equal 1 Calabi-Yau threefolds. We were looking for candidate variations of Hodge structure for mirrors to H11 equal 1 Calabi-Yau threefolds. And so once we did our classification of integral variations of Hodge structure, we actually had to go and say, well, wait a minute, which of these come from geometry, right? And the best answer we had for coming from geometry was they are mirrors of things with H11 equal 1 that we know how to construct torically. Okay, so this was a profoundly unsatisfactory answer, okay? Because what you're saying is you have something which is organic to an H21 equal 1 story, and the only way you have of figuring out what the example is that realizes it is to find an H11 equal 1 and mirror it. It's completely ridiculous, okay? So this theorem is the remedy to that. Okay? It's saying, no, in fact, there are very simple regularities in the structure of those 14, and it all comes from this internal fibration structure, and it's all very natural from a hypergeometric standpoint as well. Okay, so that's what that does. Now, of course, it motivates a fundamental question, which is, how do you classify threefolds that are fibered by lattice polarized K3s? Because obviously, if we can classify the threefolds that are fibered by these, then we subsume the list of 14 that's famous and the many, many others, because we shouldn't restrict ourselves to H21 equal 1. I'll leave that up. So threefolds fibered by L-polarized K3 surfaces. Now, for those of you who saw Alan's talk, I won't necessarily cover the same breadth as he did, but I'll give more details today. So hopefully that'll be edifying. So let's let X be a projective threefold with, at worst, terminal singularities that admits a fibration pi x to b by K3 surfaces over a smooth base curve B. Okay. So by a result of Kolar and Mori, terminal singularities in this context implies that they're isolated singular points. Okay. So let's let U in our base B be the open set over which our threefold X is smooth, and also such that the fibers of pi are smooth K3 surfaces. Okay, so because I'm not assuming that my threefold is smooth, I not only want to delete the puncture the points in the base that correspond to singular K3s, I also want to delete any points that lie underneath these isolated terminal singularities. Okay, and that's not to say that they can't coincide. Okay, but in any case, this is what I want to do. Let's let J from U to B denote the natural embedding. And let pi upper U from X upper U, I introduced that X upper U notation yet? No, so I want X upper U, well, yeah, okay, anyway, you'll see that. I'm defining it right now. X upper U to U denote the restriction of X to U. Okay, so obviously X upper U is, pi upper U inverse of U. Anyway, pi inverse of U. Okay. All right, let XP denote the fiber of pi over P in U. And let's let NS of XP denote the Néron-Severi group. Of XP. Okay. So now we have to make an assumption about polarization of the fibers. And there's a rather important distinction when it comes to polarization in the sense of families of K3s. Okay? And that distinction has to do with whether, in some sense, the classes that contribute to the polarization are acted on trivially under monodromy or have monodromy. Okay, it's a really important feature. So we will assume that pi u xu u is an L polarized family of K3 surfaces. In a sense, I'm about to define. For some non-degenerate primitive sublattice L in the K3 lattice. Okay, remember K3 is 3 copies of H and 2 copies of the negative definite E8 of signature 1 comma rho minus 1. And also that there exists a P in U such that the Néron-Severi group L, the L is actually realized as the Néron-Severi group, such that Néron-Severi of XP is isomorphic to L. Okay? And if I refer to L perp in this context, I mean the perp in the K3 lattice. So here, let's see, we say XU is an L polarized family of K3 surfaces if, okay, first of all, there exists a trivial local subsystem L of R2 pi lower star Z, such that for all P and U, the fiber LP, the H2 XP Z coefficients of L over P is a primitive sublattice of Néron-Severi XP that is isomorphic to L. Okay, and secondly, there exists a line bundle, call it script A for ample, on XU, whose restriction AP to any fiber XP is ample with C1 of AP in LP and primitive in Néron-Severi XP. Okay? So those are the technical hypotheses for the families we're considering. Really, all we're assuming is that monodromy is going to act trivially on the lattice polarization classes, and that we have sufficient fiber-wise ampleness condition globally that's determined by a single condition on the threefold. Okay? So we call such X a threefold fibered by L polarized K3 surfaces. Okay, great. All right, so now I want to assume that we have a non-isotrivial family, L polarized family. So pi u XU over U be a non-isotrivial L polarized family of K3 surfaces over a quasi-projective curve U. Okay, with P and U such that Néron-Severi of XP is isomorphic to L. Okay, so I want to define two invariants, and these are invariants we've seen before in the context of elliptic. Look at that, what a mess. In the context of elliptic surfaces. So they're the homological invariant and the functional invariant. So the first invariant is the generalized functional invariant. Okay, so it's the map G from U to the moduli space of L polarized K3s, just given by sending P to the class of XP. And the generalized homological invariant. Okay. Which is defined as follows. It's a little more complicated. So first of all, with P as before, the fiber where the Nernst severity is actually isomorphic to L, we do monodromy about a loop in pi 1 u base point P induces an automorphism of H2 xpz, and by hypothesis, this automorphism must fix Nernst severity of xp isomorphic to L. So we have an automorphism, in fact, of the perp to L, which is the transcendental lattice, okay, and then the generalized homological invariant which, remember, in the traditional setting of the homological invariant for elliptic surfaces, we had a sheaf theoretic definition, and then we had an equivalent monodromy representation theoretic definition. So here we're just defining it this way. The generalized homological invariant is the monodromy representation rho pi 1 u p to O. Okay? Now, in the context of Kodaira's theory of elliptic surfaces, he has this wonderful theorem, and extraordinarily powerful and used all the time, which is that for a basic elliptic surface, and this is not basic in the sense of V that we were talking about earlier, this is basic in the sense of an elliptic surface with section. So for an elliptic surface with section, a basic elliptic surface, qua elliptic surface with section, it is characterized up to isomorphism by fixing its functional invariant, or J invariant if you like, and homological invariant. So what we want and what we need in order to proceed with any kind of theory here is an analogous theorem. So theorem with Harder, Lewis, etc., and Thompson. Okay, let pi u x u u be a non-isotrivial L polarized family of K3 surfaces over quasi-projective U such that there exists P and U with Nernst severity xp isomorphic to L, then pi u x u over u is uniquely determined up to isomorphism by its generalized functional and homological invariants. Okay, so this is the complete analog of Kodaira's result. Okay, now also note that although it's phrased over curves, there's no specific mention of the lattice polarization being, say, rank 19. Okay, so this works just as well for threefolds that come from generalized functional invariant maps mapping into the bulk of a lattice polarized K3 moduli space of high dimension. It doesn't have to map to these modular curves coming from rank 19. Okay. So if I'm going to stay on schedule, I have about 10 minutes. Okay. And since I actually have to take my oldest daughter to the Girls Angle Math Club at MIT at 3:45, I probably will. It's the last meeting of the semester. She's got to go. So I probably will try to finish on time. But what I want to just emphasize is a few points, and I can take the last 10 minutes to do so. So this sets the stage, right? It tells you right away that all you have to do is know how to characterize the generalized functional invariant and the generalized homological invariant, and then be willing to do the hard work to pass from this story over U to the compact Calabi-Yau, and also to worry about our original hypothesis involving terminal singularities to maybe distinguish the singularity types on the threefold and apply the minimal model program in such a way that you can tell when you're smooth, okay? So this is the strategy, this is the approach one takes. So the next step, well motivated from what we did earlier and on Tuesday, and of course, no surprise to anyone who saw Alan's talk, is to specialize to MN polarized K3 fibrations. Okay. And there we get the result that any MN polarized family of K3 surfaces, pi u xu over u, for n greater than or equal to 2, is the pullback of a fundamental modular family xn over the moduli space Mn under the generalized functional invariant map. So this is that degree 2, degree 1 statement that showed up in Alan's talk. Also, it's something I mentioned at the end of, I think, of Tuesday's talk, a little bifurcation there. And the degree 1 case, well, I mean, you're literally looking at these modular curves, M sub Mn, sitting in the moduli space of M polarized K3s that we introduced last time, okay? So if you can build a model for each of them, then you're golden, because then the work you have to do boils down to understanding ramification properties of the generalized functional invariant map, and then understanding the singular fibers, sort of generalized ADE type fibers well enough in these modular families that you can understand their behavior under pullback and completion, okay? So for this, that universal normal form we introduced last time is useful. In all honesty, it's not as useful because the list is so short based on our Hodge theoretic Picard-Fuchs equation constraint that we introduced last time. There's so few possibilities to consider, it's almost easier to go case by case through the 10 possible ends and get a model for each, okay? Okay, but then the overall strategy, keying off of what we did last time, is now clear. So our pi u xu to u gives rise to our VHS of weight 2 type 111, okay? But you don't get type 111 immediately, because what you actually get is weight 2 polarized script H on R2 pi u lower star Z, okay? And then T xu is the integral local subsystem of R2 pi u lower star Z underlying the smallest integral subvariation of Hodge structure of Hx HX30, okay, which is just F2, R2, pi U lower star, Z, okay? So then this guy supports a variation of polarized Hodge structure with polarization induced from the HX. This is what's called the essential part, a la Saito and Zucker. Okay. And then if script n sub s of xu is the orthogonal complement, see how Hodge theory sees the transcendental first and the algebraic as an afterthought, and geometry sees the algebraic first and transcendental as an afterthought. So the orthogonal complement of script t xu in R2 pi u lower star z, then rationally you get a splitting. Okay? So then this is the Néron Savary xu plus t xu tensor q. Okay? So these are the classes lying in Néron Savary of xp for our p and u. And this is necessarily a trivial local subsystem of rank 19. That was by assumption. Okay. And so everything important is contained in this local system of rank 3. Okay. And this one has Hodge type 1, 1, 1, also weight 2. Okay. So now Deligne has a canonical extension to variation of Hodge structure on a compact base for J from U to RB. And Zucker, as we mentioned before, tells us that H1B J lower star T XU tensor C carries a pure polarizable Hodge structure of weight, now 1 higher, 2 plus 1, which is 3. Okay. So the basic result we apply, Hodge theoretically now, is that, theorem, and I'm skipping all the hypotheses, but we have H1U J lower star T XU tensor C embedding into H3 XC. Okay? And this is for any smooth threefold. Pi x over b. Okay? The co-kernel of this map is actually supported on the 1, 2, and 2, 1 components. So in particular, as a corollary, we get that H1U J lower star T XU is equal to H30. Okay. So you can also show that H12 and H21 Hodge numbers are trivial. So it's really sufficient to compute the rank of this guy. So suffices to compute the rank of H1U T XU. Okay? And for this, we use local monodromy data of the local system on the moduli space of Mn polarized K3s, otherwise known as X0 of n plus. Okay? So the modular uniformization, the Picard-Fuchs uniformization, if you like, is the key to the data you need to combine with properties of the generalized functional invariant to determine this rank. And once you determine this rank, you're able to constrain the Hodge number. So there's a beautiful formula that they call Poincaré's formula. We'll call it Poincaré's formula in a paper by Delangel, Muller-Stock, Van Straten and Zuo. Okay, and it allows you to relate H1 B, J lower star of a VHS to a contribution some I equal 1 to K R pi plus 2 times the genus of the base minus 1 times the rank of V, okay, where these points pi are just the punctures. They're the complement of U in the base, okay? And then this, if you let gamma I be a monodromy transformation about small loop around pi, then R of pi is defined to be the rank of the fiber over pi minus the rank of the invariant part under gamma I. Okay. And this is the prototype for those formulas I introduced last time, the ones that followed from that work of Kontsevich, Eskin, Muller, and Zurich. Since the punchline should really be said, I'm just gonna say it in words. We have constrained the possible geometry of Mn polarized K3 families with Calabi-Yau total space enough via sort of bubbling up from Picard-Fuchs differential equations information to VHS information to geometry to use Kodaira-like result and concrete knowledge of Picard-Fuchs uniformized K3 moduli spaces to complete the classification. Okay, I'll end here. Thank you.
Let's really thank Chuck for coming here for the last lecture.